Hello. So today I want to talk about the method of undetermined coefficients. This is a technique for finding solutions to non-homogeneous linear differential equations. Um, and last time we talked about the characteristic polynomial method, which is a method for finding homogeneous solutions, right, where the right-hand side is zero. Here we're talking non-homogeneous, where you can have something non-zero on the right-hand side. Now look in this theorem before we dive in to say what the method is. First, we just want to talk about what are we solving and what theory is floating around that's driving this method. Well, here's the thing. If you want a general solution to a non-homogeneous linear differential equation, so let's remind ourselves again, what do we mean when we say non-homogeneous linear differential equation? Again, we mean it has to be linear, but the right-hand side has to be zero. So say something like this. If we had, for example, and let's say it's just first order. Let's just do a first order just to keep it simple at first. So let's say y prime minus y equals x, right? This is an example of a non-homogeneous linear differential equation. Right, and what makes it non-homogeneous is that term right there, right? It's a non-zero right-hand side, right? And when I say right-hand side, what I mean, I'm assuming we put it in this form of a linear equation where the y's and the derivatives of the y's have all been put on the left. So then whatever is left, it just functions purely of x or constants on the right-hand side, right? So this is non-zero. That's what makes it non-homogeneous. Okay. So this is an example of a non-homogeneous linear DE. Okay, so the theorem here is saying that the general solution to a non-homogeneous linear DE can be constructed by doing what? Adding just one particular solution. So we're going to find one particular solution to that DE rather than finding all of them, right? And what do you add it to? You add it to the general solution of the associated homogeneous DE, right? So what do I mean by that? This is one of those things that's easiest to see in an example, right? So the general solution of the associated homogeneous DE, well, what it means is take your non-homogeneous differential equation and just throw out the right-hand side. Just set it equal to zero. Make it zero. And once you do that, then it becomes homogeneous because that was the only thing preventing it from being homogeneous before. So here is, in this example, right? I'll show you the associated homogeneous DE. So what is this? The associated homogeneous DE would be y prime minus y, and then you just do a John Goodman, right? Mark it zero. You mark it zero, then right, and that's the associated homogeneous DE. So now, how does this structure theorem look? Well, let's just observe this theorem. Sometimes people write it like this. Sometimes they'll say y. You'll see things like this: y equals yp plus yh. You'll see this so it's like y particular plus y homogeneous, right? You'll see people think of it that way. So it's like particular plus homogeneous, right? If you want to see that theorem more as a formula than a sentence, right? Sometimes people will write it that way. So let's look at it in this example, right? So in this example, y prime minus y equals x. That's a equation, even though it's not non-homogeneous, because it's only first order. So that's an equation that we can solve, right? We have a lot of tricks for first order that don't necessarily extend to higher order. But in this case, we can easily solve y prime minus y equals x, right? We could just do integrating factors or you can do power series. There's a lot of ways to do that one, right? That one's not that bad. So let's solve this. Right, y prime minus y equals x. And here I'm not doing, I haven't said yet what is method of undetermined coefficients. I'm not even doing method of undetermined coefficients yet, right? I'm just using old techniques to solve this, good old integrating factors. Just because I want to observe this theorem about what the structure of the solutions look like. So let's do this with integrating factors. And what I want to do here, of course, is multiply both sides by e to the negative x. Right, which gives me my product rule. At which point we can integrate. Right? So I get e to the minus x y equals the integral here, right, which is going to require integration by parts, right? So we do integration by parts, and we have right u and dv. Right? So I get u v minus integral v du, right? Which is negative x e to the minus x. 1, 2, 3 negatives on that term once you integrate. Right, there are 2 negatives written there, but then we're going to integrate. So the inner function gives another negative. So there are 3 total negatives. So it stays negative. And there's our integral both sides. Then lastly, what are we going to do? We're going to divide both sides by e to the minus x, or equivalently multiply both sides by e to the x, right? And at that point, we have this, and we're done. Right? So this is a general solution of a non-homogeneous linear differential equation, right? We didn't call it that back when we were doing integrating factors, but it's what it is, right? We just weren't using those terms to talk about it. But this is the general solution of this particular non-homogeneous DE. Right? So we got there a nice general solution. Now, where to from here? I want to show that what this is, you look up here in this structure theorem, that this is a particular solution to the non-homogeneous plus, right, I want to line this up with this structure theorem, plus the general solution to the associated homogeneous, right? So my claim now is that this right here, this is y sub h, that that's one way to see the structure of this solution, is that this y sub h is, this is the general solution to the associated homogeneous TE, right? While this over here is a particular solution See, and there's no constant in it. There's no, there's a constant, -1. There's no generic unknown constant, like C in it, right? That's why it's not a general solution. It's just a particular solution. It's just one function, right? That's why we're saying particular. It's just one particular solution. This is a particular solution to the non-homogeneous D. Right? I want to observe this. So observe. Right. Let's see that each of these claims are true. Right. So this is our YP, and then that next one is Y sub H. Right. So let's look at the first claim. So let's test this Y sub P equals minus X minus 1. Right. Let's check and see that this really is a particular solution to the given non-homogeneous DE. Well, yes, we can test that by just plugging in, right? Y prime minus Y equals X. So let's test this. How we always test, right? Test by plugging in. So Y prime minus Y. If I plug in YP, this becomes negative X minus 1 prime minus negative X minus 1 is negative 1 minus X is plus X minus 1 plus 1. Oh, beautiful. Okay, that's just X, which is the right-hand side of that differential equation. See, it's supposed to end in X. There's the right-hand side. Y prime minus Y equals X. Great. So this is our how we test by just plugging in that negative X minus 1, right? So sure enough, that checks out, right? Now, I also want to observe, is this Y sub H the general solution to the associated homogeneous DE? Yes, I can. And here's a very easy way to check this. Use the characteristic equation method that we talked about last time, right? So look at the what would the associated homogeneous DE be? Well, once it's homogeneous, you can use characteristic equation, right? So you take Y prime minus Y, instead of saying Y prime minus Y equals X, Y prime minus Y equals 0. Now it's homogeneous. So you can use characteristic equation. How do we build the characteristic equation? Lambda, Y's become lambdas, right? And then derivatives become powers. First derivative, 0th derivative, right? First derivative, 0th derivative becomes first power and 0th power. So the characteristic, this is our characteristic equation, right? Well, in first order, you don't have to factor. There's only one root, right? There's nothing to factor. So here the equation becomes lambda minus 1 equals 0. So lambda equals 1. So now think back to how you build the solution based on that. Y equals e to the lambda x. Oh, there we go. There's our solution based on lambda equals 1. Right, so it's our solution for that value of lambda. But here it's the only value of lambda. But you still get to do superposition. Now that might sound a little bit funny because superposition is where you add different solutions together. But there's more to it, right? You don't just get to add solutions together. What else do you get to do? Go ahead. Yes, exactly right. You also get to multiply them by constants. So if there's one solution, you don't get to add it to anything, but you still get to multiply by a constant. So there's our general homogeneous solution, C e to the x. Right? There it is. That's exactly what we have up here. See, C e to the x. Right. So that's what's really, really nice about this is notice this method. I went through all the details here because it's fairly recently that we just looked at characteristic equations, but this method is very, very quick and easy, right? In the scheme of things, this characteristic equation method in terms of what you're accomplishing. Up here, right? So this y sub h piece is really, really efficient to find. So then if we could just have an efficient way to find the y sub p, we'd have a really nice way to solve this equation, right? One that's almost probably as easy, if not easier, than integrating factors, if we could just find that particular solution, right? And what's nice about this is it extends to higher order equations. Integrating factors works great for first order, but it doesn't extend to higher order equations, right? At least not in a natural way. So that's the big question now is, can we, how would we find this, right? Here I found it by cheating. I did integrating factors, right? I used some other method of solution to find the particular solution, right? And then I just plugged it in and tested it was correct. So that's the $1,000,000 question now, is how would I find this from scratch? And then I don't have to rely on integrating factors. And then I could use this method for second order equations, third order equations, and so on, right? Well, that's our question, right? The $1,000,000 question is, how could we have found that particular solution without having cheated by using integrating factors, right? Because I don't want to rely on integrating factors. As I mentioned, then we're stuck only being able to apply this to first order equations, right? So how else could I have found that particular solution? Well, this is where we finally made it to the title of today's session. The method of undetermined coefficients comes in. What this is this is a very, very fancy name for guess and check. As we often do in differential equations, you guess the form of the solution with some unknowns plugged in, and then plug it into the DE and see what those unknowns must be, right? So that's the answer here, right? The answer is method of undetermined coefficients, which is just strategic guess and check. And I'll show you in this example how it right, so just strategic guess and check. So here is in this case what you would do. So you'd say, okay, y prime minus y equals x. So I look on the right hand side, and here's what I mean about strategic. You say, what is on the right hand side? Well, there's a degree 1 polynomial. X is a degree 1 polynomial. So you know what I'm going to guess for my particular solution? I'm going to guess a degree 1 polynomial. Right? Because, I mean, if you're going to take a function, take its derivative, and subtract that original function and end up with x, you probably had to start with some sort of constants and powers of x, and right, you probably didn't end up with an x by starting with, I don't know, cosine on that left hand side, right? Then there'd probably be a sine or a cosine on the right hand side. So that's the idea. You just sort of guess a similar form, plug it in, and hopefully it works. So that's what I'm going to do. I guess this this ax plus b for our particular. So I'm going to plug that in. Right, and simplify. And we get negative ax plus a minus b for the cleaned up version of that left-hand side. Now here, what does it have to equal? It has to equal x, right? Because I want this to be a solution to that differential equation. Okay, now what is x? X is really 1x plus 0. And I'm writing it that way because I want these to be in the same form. Constant times x plus constant, right? Because that now gives me two equations. I can now equate the degree 1 coefficients, and I can equate the degree 0 coefficients. Very similar to what you do when you're solving a differential equation using power series, right? And you expand everything out and then equate coefficient by coefficient. Or very similar sometimes when you're solving partial fraction decomposition. Sometimes you'll work this way. Expand everything out and then equate the coefficients. Same idea. So the degree 1 coefficients, that's just that negative a equals 1. The degree 0 coefficients, that's a minus b equals 0. Okay. So now I have a equals minus 1, which tells me that b has to also equal minus 1 because their difference is 0, so they're equal. Right? And once again, where are these pulling from? Well, here I have, right, I have this degree 1 coefficient is just saying the degree 1 coefficient of the left-hand side of the differential equation has to equal the degree 1 coefficient of the right-hand side, while the degree 0 is saying that the degree 0 coefficient of the left-hand side of the differential equation has to equal the degree 0 coefficient of the right-hand side. So that's where we get those two equations from. And now look, a equals minus 1, b equals minus 1. Put those back in to our y sub p, right? Our particular solution is negative 1 x minus 1, which is what we found by integrating factors. But here I didn't solve the whole differential equation. Here I only solved for that particular solution, right? So this is now the idea, is we now have a full way that I could have solved this differential equation without using integrating factors, right? Given this y prime minus y equals x, what could I have done? I could have found y sub h equals c e to the x via the characteristic equation, right? And then I could have found that y sub p equals negative x minus 1 via method of undetermined coefficients. I was trying to write muck, and I wrote moo. Until I have a toddler. Everything is animal sounds or graham crackers. So the right, there's our characteristic equation and our method of undetermined coefficients. Then what do I do? Well, then we go back up to that theorem, right? The theorem that I started with. The theorem that says that to get your general solution for a non-homogeneous equation, just add together a particular solution and the general solution to the homogeneous associated homogeneous equation, right? So then we apply the theorem and we're done, right? The general solution is y equals yp plus yh, which is minus x minus 1 plus c e to the x, right? This is our result. So that's, and now I'm not rewriting the details of the characteristic equation method there, or rewriting the details of a method of undetermined coefficients there, because those are up above, right? But this is now, now we have kind of a complete standalone method that doesn't require, it doesn't lean on the equation being first order, right? That's what's really nice here is method of undetermined coefficients will work the same for higher orders. It'll be messier, but it'll work the same. Characteristic equation works the same for higher orders. It's messier, but it works the same, right? So that's why this method is so nice, even though we could have even already solved this differential equation via integrating factors, right? So that's our first example that I wanted to go through. So it's an equation we could have already solved, right? But I wanted to show it with this new technique, with this this particular plus homogeneous theorem, right? Getting the homogeneous from characteristic equation and the particular from method of undetermined coefficients, right? Okay, so let's do another example, right? And we'll do one that's a little bit heavier. So let's do this. Let's solve. This is one that we could definitely not solve by integrating factors. Let's solve y double prime. Let's say plus 2y prime plus y equals cosine x. Right, let's solve this differential equation. So here's the idea. This is a linear, non-homogeneous equation, right? So we're going to solve it in 2 steps. We're going to solve it by getting a particular solution, right? This is one step. We're going to do this via method of undetermined coefficients, right? And this side, we're going to get via characteristic polynomial or characteristic equation, right? So this is our plan. Now, let's start with the characteristic equation. All right, so what do I do there? Lambda squared plus 2 lambda plus 1 equals 0. Factor that. So I get lambda plus 1 squared equals 0. So my solutions are lambda. So it's a double root at -1. Let me say that before I say the solutions. All right, so this is double root at lambda equals -1. So the solutions, we get 2 solutions, which are e to the minus x and x e to the minus x, right? Lastly, we do superposition. And that shows us that it's c1 e to the minus x plus c2 x e to the minus x. And there we go. And I'm going to put an h there because it's not y in the same y from the original equation, but y sub h is maybe the best way to say that, right? Because it's the homogeneous, it's the associated homogeneous equation. So that's, and notice when I did the characteristic here, right? How did I get that characteristic equation? Well, on the left-hand side, the y double prime becomes lambda squared, right? Y prime becomes lambda. Y becomes basically lambda to the 0, right? 0th derivative. So it becomes just 1. And then what happened on the cosine? Well, I just made it 0. Why did I make it 0? Because that's what it means, the associated homogeneous equation, right? Right-hand side, mark it 0. So that's our system for building that characteristic equation, right? So we already have y sub h. Now I want y sub p. Okay. So method of undetermined coefficients to find y sub p. So we need to ask ourselves what we should guess. Well, look at that left-hand side. Y double prime plus 2y prime plus y equals cosine of x. Okay. So I'm going to take some function, take a bunch of derivatives of it, multiply it by some constants, add them together, and I'm going to end up with cosine. All right, well, what must I have started with? I probably started with a cosine, right? Or maybe, you know what else might have been there? It could have been a sine, right? Because sine also, when you take derivatives of sine, becomes cosine if you take the right number of derivatives, right? So that's going to be my guess for this particular solution. Some combination of sines and cosines, right? That's what I see on the right-hand side. I see cosine. So probably sines and or cosines on the left-hand side got plugged in order to create that. So that's going to be my guess. So we plug this in now on the left-hand side. So on that left-hand side, what do I have? I have y double prime plus 2y prime plus y equals what? So I want the second derivative of these terms. So what's the second derivative of a cosine? It's going to be negative a cosine, right? The second derivative of cosine is negative cosine. Similarly for sine. Second derivative of sine is negative sine. So there we go. There we have our y double prime terms. Now let's plug in for plus 2y prime. Okay, so y prime of a negative a sine, right, plus b cosine. Because I'm just taking now a first derivative. Right? And then I have just y. So for y, I just copy it down. Right? A cosine plus b sine. Okay. And let's simplify, combine like terms a little bit, right? So here, what do I have? I have cosines and I have sines. Right? So let's gather up all the cosines. So what are all the coefficients of the cosines? I have a negative a, I have a 2b, and I have another a. Right? I have an orange negative a, green 2b, and a purple a. And then for sines, what do I have? I have negative b, negative 2a, and b for sine. Right. So this actually cancels even a little bit better. I have 2b cosine, and then I have negative 2a sine. Right. What is this supposed to be? After I plug it in, it's supposed to give me cosine of x. Right? So this all equals cosine of x, which is better known as 1 cosine x plus 0 sine of x. All right, just like before, equate the coefficients of corresponding terms, right? The only way these expressions are going to be equal is if 2b and 1 are equal, and if negative 2a and 0 are equal, right? So b has to be 1/2, and a has to be 0. So now plug those back in to y sub p, right? And I get my particular solution. Yp equals, so a is 0, so 0 cosine x, right, plus b sine. Okay, there's our y sub p, is 1/2 sine x. Great. I just got my y sub p. Now I'm ready to build the general solution. So we just figured out the general solution to the original differential equation, y double prime plus 2y prime plus y equals cosine x is what? So y of x equals y sub p plus y of h, which is our particular solution now, 1/2 sine x, right, plus y sub h, which was e to the minus x, or sorry, c1 e to the minus x, plus c2 x e to the minus x. Right? And Here, C1 and C2, of course, can roam across all real numbers. And we did it. All right, so we found the general solution to this differential equation. And notice I didn't appeal to any other technique like integrating factors, the first example, right? It was a second order equation. I didn't have options like integrating factors, right? So here, what did I do? I said it's a second order linear differential equation. It's non-homogeneous. So I'll break the solution into two steps, finding the particular solution and finding the homogeneous solution. How do I find the particular solution? I do the strategic guess and check. I do method of undetermined coefficients. How do I find a homogeneous solution? I throw away the right-hand side, I make it 0. I get the characteristic equation, and that gives me the homogeneous solution. Then I just add them together, right? Once you have the homogeneous and the particular, you add them together, and that's your general solution, right? So there we go. That's the method for undetermined coefficients, right? For solving non-homogeneous differential equations. There are some weirder hiccups that can happen, and you'll see those soon in another video. So it doesn't always go as smoothly as the example I showed here. So I'll show more of the special cases in our next video. So thanks.